I am so thrilled that you are interested in visiting this channel. You should sense this knowledge is beyond your hard work. Believe that if you understand the problem, the solution will find their way towards it. I have poured my heart and soul in making this video that most of the students should be benefited through this channel. That's the belief I sleep with, and that's the belief I wake up with. And today's video is on group theory, and there are four problems which are flashing on the screen. The first thing is, in a group G dot, we have to show that AB inverse is equal to B inverse into A inverse. So these are the most important questions. And in a group G, each element has its own inverse. Then we have to show that G is abelian. In a group G dot, A square is equal to E for every A belongs to G. Then we have to show that again G is abelian. Next one, the fourth question here is, in a group G dot, the only idempotent element is the identity element. So there is a slight difference, idempotent, and this is identity. So let's get started to solve the first question here. So here it is given that G is a group. So if it is a group, it already satisfies four properties. One is closure, associativity, identity, and inverse. And we have to use all the four properties, and we have to show that AB whole inverse is equal to B inverse into A inverse. See how easy it is. So what is given? Given G dot is a group. Clear? If it is a group, it is very clear that it satisfies closure, associativity, identity, and inverse. Now I am taking the inverse property. See here. So what is the inverse property? Inverse property is nothing but if A belongs to G, then A into B is equal to E is equal to B into A. Then we say that A inverse value is equal to B. See here. If A belongs to G, and according to inverse property, if AB is equal to E is equal to BA, then we show that A inverse is equal to B. And I am going to apply here. So here A inverse is equal to B. See here A inverse is equal to B. And now we have to multiply these two. So in order to show this, what I am going to do? So I am going to multiply with. So consider this whole thing as A and this whole thing as B. Then we have to make A into B. So now this is A and the B value here is B inverse into A inverse. If I take two elements, for every A comma B belongs to G. So I'm considering these two. And this will be A into B inverse into A inverse. So already it satisfies the inverse property. Then according to the identity law, B into B inverse value is equal to E, which is equal to A inverse. So here A into E according to the identity law, which is equal to A into A inverse. A inverse is equal to E. As A belongs to G, then A into A inverse is equal to identity element. And therefore we got AB into B inverse into A inverse is equal to E. So this is equation number 1. And now I am going to multiply. Now this time A into B and this time B into A. This time I have to multiply B into A. So here what is B value? That is B inverse into A inverse into this value is AB. And now if I multiply, this will be B inverse into, I am joining these two, that is A inverse into A into B. So here A inverse into A value is equal to identity element, which is equal to B. So if I multiply with the identity element B inverse into B, so here B inverse into B is again nothing but the identity element. Therefore, we got B inverse into A inverse into AB value is equal to E. So this is equation number 2. So from 1 and 2, see here what I am writing. From equation 1 and equation 2. So here, what happened here? AB into, see here, AB into, this is B inverse into A inverse is equal to E, which is equal to, this is B inverse into A inverse into AB. Therefore, AB, so this is of the form AB is equal to E. See here, this is AB is equal to E, which is equal to BA. So if you observe AB into E is equal to B into A, then we say that A inverse is equal to, the value here is B. So clear. So this is how we have to prove, and this is so simple if you follow the inverse property and identity property here. First I have taken two elements, A comma B belongs to G. So as G is a group, it satisfies the inverse law. According to the inverse property, A into B is equal to E is equal to B into A. Then we say that A inverse is equal to B. So among these two, I have to prove AB whole inverse is equal to B inverse into A inverse. So this is A inverse is equal to B. So I have to multiply AB and check. So if I multiply A into B, I got the identity element, and after multiplying here as B into A, I got again identity element. Therefore from 1 and 2, so A into B is equal to E is equal to B into A, and we say that A inverse is equal to B. So this is how we have to show. This is so simple. And the next question here is, so this one is completed. In a group G, each element has its own inverse. Then we have to prove that G is abelian. So each element is having own inverse here. A is having its own inverse, B is having its own inverse, and here it is given that G dot is a group and it's having an own inverse, and we have to show that G is abelian group. And for in this case, so here what is given? G is a group. Let given that G dot is a group. The first thing is G dot is a group, and it is also shown that each element has its own inverse. So it is also given that each element has its own inverse. Let A comma B belongs to G. So if A belongs to G and A is having its own inverse, which implies that A inverse is equal to A. So if A inverse is equal to A and also B belongs to G and every element in G has its own inverse. So B is having as B as an inverse. It is having own inverse. Therefore, A inverse is equal to A and B inverse is equal to B. And now what we have to show, it is abelian. Already it is a group. So if it is a group, all the four properties are satisfied. One is closure, associativity, identity, inverse are already exists. And what is the extra property which we have to show? It's a commutative law. So commutative law is nothing but AB is equal to BA. And now we have to consider, see here, now I am taking two elements here. Let A belongs to G and next B belongs to G, and according to the closure law, AB belongs to G. See here, according to the closure law, A into B belongs to G. So every element has its inverse, and therefore AB whole inverse is again equals to AB. And according to our question, every element has its own inverse. So AB whole inverse is nothing but B inverse into A inverse, which is equal to AB. So now I have shown that B is having its own inverse and A is having its own inverse. Therefore, in place of B inverse, I can write B, and in place of A, I can write as A, and which is equal to AB. And therefore, for every A comma B belongs to G, AB is equal to, this is BA, and therefore G is commutative. G is commutative, and already it is a group, and if it's a commutative and all the five properties holds, and we finally conclude that G is an abelian group. Therefore G is abelian. See here, it's very easy if you see. So it is given that G is a group. So it is given that G is a group, and it is also given that each element has its own inverse. Each element has its own inverse. If I take A belongs to G, then A inverse is equal to A. If I take B belongs to G, then B inverse is equal to B. And now we have to show that G is abelian. So if it satisfies the commutative law, according to the group we have already four properties, and according to this commutative property, all the five properties holds, and we say that it is an abelian group. And therefore, I have taken two elements, and according to the closure law, AB is equal to B. As AB belongs to B, it's having an own inverse. AB inverse is equal to AB. So this can be written as B inverse into A inverse is equal to AB. Already we know that B inverse value is equal to B and A inverse value is equal to A. And now we got, after taking two elements from G, AB is equal to BA, and therefore G is commutative. And finally we say that G is abelian. So clear. And the third question here is, in a group G, if A square is equal to E, if A square is equal to E, for every A belongs to G, then we have to show that G is abelian. So it is given that A square is equal to E. See, what is given? G is a group. So G is group given, and A square is equal to A is given, and we have to show that G is a group here. And now see here, What is given? G dot is a group. Clear? So if it is a group, all the four properties satisfies. And it is also given that A square is equal to E for every A belongs to G. These are the two conditions given, and we have to now prove that. G is an abelian group, and again we have to show it's a commutative law. And see, if I take two elements from this group G, let A comma B belongs to G. Let A comma B belongs to G. If A belongs to G implies A square is equal to E. Then we can write that A into A is equal to E. So according to a group, according to our inverse law, see here, if you remember this inverse law, if A belongs to G, B belongs to G, AB is equal to E is equal to B into A, then we say that A inverse is equal to B. So according to our inverse law. So if you observe that, if you take A for 2 times and A into B is equal to E, then we say that A inverse value is equal to A. A inverse value is equal to A. So keep it aside. And next one, if I take B as an element. So if you take B from a group G, then we have B square is equal to E. So we can write it as B into B is equal to E. So if two things are multiplied and it is equated to E, then we say that the first element is the inverse of the second element. Therefore, B inverse is equal to B. Clear? So now what we have to show? We have to show the commutative law. And together I'll take let A belongs to G and B belongs to G implies A dot B belongs to G according to the closure property. So if A into B belongs to G and we say that AB whole square belongs to, A square is equal to E here. A square is equal to E. And therefore, if A square is equal to E, then we can write AB into AB is equal to E. And what we say here, if A into B is equal to E, then A inverse is equal to B. And therefore, AB whole inverse value is equal to AB. And therefore, AB whole inverse value is B inverse into A inverse is equal to AB. So we know that B inverse is equal to B and A inverse is equal to A. So in place of B inverse I am writing B, in place of A inverse I am writing A, and this is AB. And therefore, and finally we got for A comma B belongs to G, we got AB is equal to BA. Therefore, G is commutative. So G is a commutative law. So AB is equal to here, it is BA. Therefore, G is abelian. Therefore, G is abelian group. See here, let me tell you once again, G dot is a group and A square is equal to A for every A belongs to G. So if I take two elements, if A belongs to G, A square is equal to E, then A into A is equal to E. So according to the inverse law, A inverse is equal to A. If B belongs to G, B square is equal to E and B dot B is equal to E. Therefore, B inverse is equal to B. And now already it is a group, it satisfies four properties, and along with that, if it satisfies commutative law, then G will be abelian group. And now for showing it to satisfy commutative law, I have taken two elements, A belongs to B, B belongs to G. And according to the closure law, A into B belongs to G. If AB belongs to G, then A square is equal to E. AB whole square is equal to, this is equal to E. Therefore, AB whole square is equal to E can be written as AB into AB, which is equal to E. So here, if A into B is equal to E, if A into B is equal to E, A inverse value is equal to B. And therefore, this is A inverse value is equal to the second term, this is B. This can be written as B inverse into A inverse is equal to AB. B inverse value is B and A inverse value is equal to A, and AB is equal to BA. And this is nothing but the commutative law. And G is already a group and G is commutative, and therefore we say that G is abelian. So G is an abelian group. And the last question here is, in a group G, the only idempotent element is the identity element. So this is also so simple. So what is given? G dot is a given. The only idempotent element is the identity element. So in this, see here, what is given? In the solution, G is a group. So given G dot is a group. And next one, let E be the identity element. Let E be the Let E be the identity element. Suppose A is it's an identity element, it's an idempotent element. It's an idempotent, let A be an idempotent element. If it's an idempotent element in group G, then A square value is equal to A again for every A belongs to G. So according to idempotent element. So this can be written as A dot A is equal to A again. So this can be written as A dot A is equal to A into E. So according to the left cancellation law, A value is equal to E. So if A value is equal to E, then we say that A is an idempotent element, E is the identity element. Therefore, the only idempotent element is the identity element. See here, in a group G dot. In a group G comma dot. So A is nothing but the idempotent element and E is nothing but the identity element in the group G dot. And this is how we have to show. And in a group G dot, the only idempotent element is the identity element. Let G dot be a group, E be the identity element, and A is an idempotent element. If it's an idempotent element, A square is equal to A dot A is equal to A. So if I write it in the form A into E and cancelled A from the left side, therefore A is equal to E, and A is nothing but the idempotent element and E is nothing but identity element, and G is a group. So finally we conclude that in a group G dot, the only idempotent element is the identity element. So this is how we have to solve each and every question. These are very, very important, repeatedly asked questions, and hope you guys understand. If you really understand, you know what to do. Please raise your thumb, pass it on to your friends, subscribe to this channel, stay connected. So many theorems and solutions are uploaded in this video, and it will be very, very helpful and very easy to solve. Go through the playlist, pass it on to your friends, and thank you for staying till the end.